If you want your Spark applications to run well, you are probably going to have to think about partitioning at some point. And there are two parameters that we can set when we're doing that optimization. One is the number of partitions, and the other is the partitioner itself. When we set the number of partitions, we're going to be making a trade-off between task execution time, in the case of a large number of partitions, and making optimal use of parallelism in the case of a low number of partitions. We'll have to look in some detail about the different partitioners and when to apply each one of those. And how many partitions is enough? Well, like I said, if you have too few, you have a few things that can go wrong. Number one, you might not be taking proper advantage of the parallelism you have in your cluster. There could be workers that you could be using that you're not using. You also might get the problem of data skew, where one partition ends up being larger than another. You don't have a good uniform partition size. With large partitions, you can have increased pressure on RAM, on memory usage, and you also might find that failure takes a long time to recover from. So you don't want the partition count to be too small. On the other hand, you don't want the partition count to be too high. Remember, a partition is a task. Spark will allocate a single task to run on a single executor to process that partition. And there's overhead in scheduling that work. You don't want to incur too much overhead for tiny little bits of computational work. You don't want too many partitions, you don't want too few. And those trade-offs are nice, but you might be wondering, no, seriously, how many partitions should I have? Well, the published guidelines say at least 100 and no more than 10,000. You might not find that to be a very helpful range, so let me give you a few more guidelines. On your lower bound, you want your partition count to be at least 2x the number of cores that are available to your Spark application. On the upper bound, you want to make sure each task execution time is at least 100 milliseconds. That's a thing you're going to have to observe. You can't predict that by looking at a core count. But in looking at the application web UI, you'll be able to see those execution times and get an idea, as we show here in this screenshot, whether you're spending too much time coordinating and moving tasks around and moving work around and not enough time doing actual computation. Now, as you may recall from our earlier treatment of partitioning, not every operation, not every transformation or action even requires a partitioner. They may return none when you look at their partitioner. Some, however, do, and let's take a look at those. Operations like the ones we show here, reduce by key, fold by key, combine by key, cogroup, join, you may notice those all have something in common. Those are key-based operations. Those all require the hash partitioner. The range partitioner is required only by sort by key. Since the RDD that comes out of that is going to be ordered, it needs a partitioner that's able to preserve that order. And remember, you can provide a custom partitioner. This is something the Spark-Cassandra Connector does for efficiently dealing with data that comes from Cassandra and is going to Cassandra. So implementing a custom partitioner is something that's very much available to you. We're not going to cover it in this course, but it is a documented thing and it might be of interest to you. So check it out if you think it is. Let's take a look at maybe a suboptimal case of a Spark application that didn't use partitioners well, and then how we might change that. On the left, you see the suboptimal case. We start with some RDD called RDD1, and we're applying two key-based transformations to it, and then performing one key-based action. All right, so those two key-based transformations are going to create two new pair RDDs, on which we'll then run an action and produce an output. And on the bottom, you see the key-based action produces its own output. Now, each key-based transformation or action will result in a shuffle. And remember, we don't like shuffles at all. Shuffles are one of our biggest costs, probably our biggest cost in creating a Spark application. They require moving data around the network between workers, and we want to avoid that. So 3 unearned shuffles in one application is not a good thing. If we look at the diagram on the right, you'll see we proactively shuffle that partition ahead of time, or we intentionally set a partitioner on RDD1 and create what we call RDD1 prime. In terms of the data itself, we haven't done any transformation to it. It doesn't look like that RDD contains anything differently, but we've done the partition, which means we have incurred one shuffle at the beginning of the job to create that new RDD, that partitioned RDD to work with. We then perform those two key-based transformations, making RDD2 and RDD3, and the key-based action on the bottom, none of which requires another shuffle. So we take 1 instead of 3, and that is a huge performance win. So understanding partitioners and taking control of them can make your applications run a lot faster. So what are the actual mechanisms we have to take control of partitioning? Well, there are some at the application level, there are some at the operation level, and there's some intentional transformations that we can apply that will cause repartitioning in the way we want. At the application level, there are properties like Spark default parallelism that's going to determine the value of the default parallelism property in the Spark context. We also have the Spark-Cassandra input split size in megabytes, which determines the largest possible size of a partition for an RDD that's coming from a Cassandra query. Now, by default, this is 64 megabytes. If you'd like that to be different, you can change this parameter. Many transformation and action calls take an optional parameter called num tasks. Now, task is synonymous with partition. Since one task will always be allocated to process one partition, if you pass that parameter in when you call a transformation, then the RDD you get out will have that number of partitions. So you're able to set that on a transformation by transformation basis. Interestingly, even the parallelize method has the num tasks parameter. If you recall, that's the method you call in the Spark context when you want to take a static collection that you've created and turn it into an RDD. So even then, you can specify the number of partitions you'd like. Finally, there are a few special methods that explicitly cause repartitioning of an RDD. Let's take a look at those in detail. Calling the repartition method on an RDD creates a new RDD that has the number of partitions you specify. That's all it does. You can make the number larger, you can make the number smaller. That new RDD also has the partitioner of none. Now, doing this will cause shuffling. It has to. So this is an expensive operation, but it might be worth it, as we saw in the example before, to take this hit up front before subsequent operations cause their own shuffles in a less controlled way. Coalesce is a lot like repartition, except when we're shrinking the number of partitions, coalesce might let us get away with that without a shuffle. So if you have an RDD whose number of partitions you want to reduce, call coalesce, and what that will do is merge some of those partitions together without incurring the penalty of a shuffle over the whole data set. And you can see here an example of some of these things being called. And I encourage you again, if you've got a Spark shell running, try these things out with some of the test data, watch them work, make sure you get the same results back, the same partition counts you see in the code. If you want to repartition a pair RDD, or an RDD containing key value pairs, you use the partitionBy method. This is a little pickier in that we have to explicitly tell it which partitioner we want to use, so we have to know something about which one to pick. Let's take a look at the rules. In most cases, you're going to use the hash partitioner, and you see in the code here that you'll create a new instance of the hash partitioner and pass to its constructor the number of partitions that you want to use. So you're telling it the number of partitions, you're telling it the partitioner to use. If you've got an RDD that you know you're going to sort in the future, and maybe sort more than once, then you want to use the range partitioner. That's going to allow you to pre-partition it with a partitioner that's friendly to ordering. And so that way, future sort calls, even if there's more than one of them, won't require a shuffle. And remember, we're showing the two standard partitioners, hash and range. This could always be a custom partitioner if you've got one. Let's take a look at some code that does this poorly and then some code that does it well. So what we have here is a query from a Cassandra table, getting the records from the movies table, making a pair RDD out of them organized by release year. Then we're going to repartition that by twice the default parallelism, probably twice the number of cores is what we're doing there. Then we're going to do a count by key, and in the next line, a group by key. Now the repartitioning causes a shuffle, the count by key causes a shuffle, the group by key causes a shuffle. That's not efficient. We would prefer just to shuffle once. In the optimized code, we do the same query, we make the same pair RDD. We're looking at all the movies organized by release year, but now we partition by. We call partition by because it's a pair RDD. We tell it we want the hash partitioner with the same number of partitions as the suboptimal version, but we've pre-partitioned it with the hash partitioner. Now our call to count by key and group by key won't kick off a shuffle and won't require repartitioning. So we've just taken that expensive shuffle operation one time by thinking ahead and doing the partitioning the right way.